Alright, so the example we're going to work through here in linear programming says that we're going to try to maximize this function z equals 5x plus 3y subject to this whole string of inequalities. There's a bunch of things there. One thing I want to mention is that when you see these linear programming problems in your book and in my math lab, they're not going to show the inequalities in the same I don't know, structure as a system of equations where we list them, we stack them vertically and put that little squiggly brace on the left side. Instead, they're just going to write them in a row here. It doesn't matter how they display them. The idea is the same. It's just a set of inequalities. One thing that is very important to notice, we have this x greater than or equal to 0 and y greater than or equal to 0. It's the same combination we saw in the last section that gave us a first quadrant graph. Okay, so notice if x is greater than or equal to 0, it's everything to the right of the y-axis, and y greater than or equal to 0 is everything above the x-axis. And so those two combinations give us quadrant 1. So we know our graph is going to be in there. The other three inequalities will be fairly simple to graph now that we can restrict ourselves to just quadrant 1. Okay, so let's go ahead and start sketching this out. The x plus y is greater than or equal to 2. Think about that as a line without the greater than, just x plus y equals 2. Then the x-intercept, if I cover up the y, the x-intercept is 2, and the y-intercept is also 2. Okay, so that gives us a constraint. It's a solid line because of the equal sign. In fact, pretty much all of these are going to have equal signs, so we can stick with solid lines here. Okay. Now the next thing, the next equation, x plus y is less than or equal to 8. So again, the x-intercept is 8, and the y-intercept is also 8. And so I'm going to count 8 in each direction. So 2, 4, 6, 8. 2, 4, 6, 8. And then sketch the graph through those. Alright, then I should probably shade each of these inequalities as we go. At least get the idea of where the shading is going to need to go. So with the x plus y is greater than or equal to 2, I'll go back to that one. I'm going to do a test point of 0, 0. Okay? If you plug in 0, 0, 0 plus 0, you get 0. That is not greater than or equal to 2. In fact, it's less than 2. And so my test point cannot be in the solution to this inequality, so I'm going to need to shade everything up and to the right of that inequality. I'm going to hold off on actually shading it till the end. Alright, I'm going to do the same test point for the second equation. You get 0 plus 0, which is 0, and that is definitely less than or equal to 8. That one is true. So on the second inequality, or second equation, I'm going to shade the side that is toward the origin. Okay, so that would be down to the left. And then finally, this last one, the y-intercept is 10. So y-intercept is up here at 10. The x-intercept, if I cover up the y, put a 0 in for y, the x-intercept will end up being 5 because I have to divide out the 2. So 2, 3, 4, 5 right there. And I can sketch the graph through that. Let me grab a separate piece of paper here to sketch that through. Give myself a straight edge. That's not too bad. All right, and then on that one, I've got to figure out what the solution is. So I've got to do another test point. So I got 2 times 0 plus 0. Well, that's of course 0, which is definitely less than or equal to 10. So I want to shade the side that includes the origin, which would be down and to the left again. And so the only region that's contained in all three of those inequalities, in addition to the first quadrant, is going to be this, whatever this shape is here. Let's say 1, 2, 3, 4, 5. It's a 5-sided shape. And so what I want to do then is I want to maximize this objective function over that region. To do that, I need to plug in some points. Remember I said in the previous video that if you were to plug in every point in this region, the maximum value will always end up on a corner. And that's just because this is a linear function, right? Each of these variables is raised to the 1 power. If it was not linear, if you had other things going on like a 5x squared or an x times y or something, then your maximum and minimum could occur somewhere else in this region, maybe on an edge, maybe in the middle. But with a linear one, it's always going to end up on a corner. So what I want to do is find all the coordinates of the 5 corners. Some of them are pretty obvious. This one down here is going to be 2, 0. This one is 5, 0. This one is 0, 2. This one is 0, what's that, 8? And so the only one I don't know is this one here. And that is going to be the point found by intersecting or solving the system that contains, let's see, it'd be these last two, right? So it'd be x plus y equals 8 and 2x plus y equals 10. I want to solve that system to find the intersection point. Well, real quickly, I could just solve for y here. So y, I'll do a substitution method. Y is equal to 8 minus x. I sub that in. 2x plus, then the y becomes 8 minus x equals 10. Let's see, 2x minus x is x. Subtract the 8 over, and I get x is equal to 2. Oh, that makes sense, I guess, just for my grid lines. And that would mean that y then, if I plug a 2 in, 8 minus 2 would be 6. So y must equal 6. So that point of intersection is at 2, 6 there. Which looks about right just from the graph. Finally, I have to take all 5 of these points, plug them in to the objective function, and see which one gives me the largest value. Okay, so I'll list off all these points. We'll start at 2, 0. We'll do, scoot that up. We'll do 5, 0. We'll do 2, 6. We'll do 0, 8. And we'll do 0, 2. So those are all 5 of my corners. Alright, so z must equal 5. So it's 5x, can't see that? 5x plus 3, right? So I want 5 times the x value plus 3 times the y value. That 0 drops that off, you get 10. Alright, we're just going to keep that in mind and compare it at the end. 5, 0. So let's do z equals 5 times 5 plus 3 times 0. That term's gone. 5 times 5 is 25. Now since we're maximizing, whoops, can't see that. Since we're maximizing, we want the largest value. I can already discount the first one because the second one is bigger. Okay, so it's not going to be that first point. Next, z equals 5 times 2 plus 3 times 6. This is definitely bigger. 5 times 2 is 10. 3 times 6 is 18. That's going to be what, 28? All right, and 28 being bigger than the previous two numbers will eliminate one of them. 0, comma 8 is an interesting one. That's 5 times 0 plus 3 times 8. This term disappears. 3 times 8 is 24. That's not quite as big as the 28, so that one doesn't factor in. And then finally the 0, comma 2. That's 5 times 0 plus 3 times 2. 5 times 0 is gone. 3 times 2 is 6. That's definitely not the largest because the 28 is now the largest. So the final answer then is that we would say the max value of z equals 5x plus 3y is 28 at the point 26. Okay. So the max value of that function is 28 at the point 26. Okay. So just remember, you have to plot out the constraint inequalities and plot out the intersection of their regions. Find all the corner points. Either you can just get them right off the graph, or you can do a little bit of work to find them. And then you plug each of those each of those corner points in to the objective function, and just simply see which one is biggest. Here's 28 by maximizing. Okay, that's it. If you're minimizing, then you just look for the smallest value at the end. So 6 here would be the smallest value.